planetary solar masses? Gone. Not destroyed, not scattered, converted in less than a second into pure ripples of reality itself. That's what happened 1.3 billion years ago when two black holes finally stopped circling each other and became one. The collision didn't make a sound. It didn't create a flash of light. It didn't leave wreckage floating through space. It did something far stranger. It shook the very fabric of the universe so violently that, a billion years later, two laser beams in rural Louisiana trembled by a distance 1/10,000th the width of a proton. And scientists lost their minds, because what those lasers detected wasn't just a signal. It was a message, written in the language of warped space-time, sent from a catastrophe so extreme that the physics we use to describe reality simply breaks down at its center. We couldn't read that language until 2015. And now that we can, what we're hearing is deeply, profoundly unsettling. This isn't a story about black holes colliding, it's a story about what we found hiding inside that collision, a signal that shouldn't exist, an echo that rewrites what we thought we knew, and a question at the end that no physicist on Earth can currently answer. Stay with me, because this goes somewhere you're not expecting. First, let's make sure you understand what we're actually dealing with. Forget everything you think you know about black holes as objects. They are not cosmic vacuum cleaners. They are not giant space drains. That mental image, satisfying as it is wrong in a way that matters. A black hole is not a thing. It's a condition. A region where space-time itself has been so catastrophically distorted that the normal geometry of the universe ceases to function. Here's what that actually means. You live inside a universe that has shape, not shape like a box or a sphere, shape in a deeper sense. The three dimensions of space and the one dimension of time are woven together into a single continuous fabric. Physicists call it space-time. And that fabric is not rigid. It bends. It curves. It flexes. Every object with mass deforms it. The Earth, the Sun, you, sitting wherever you are right now, you're bending space-time. Just by existing, now imagine what happens when you don't just bend it, but collapse it. When a star, many times more massive than our Sun, runs out of fuel, the outward pressure that kept it inflated disappears, and gravity, which has been waiting patiently for billions of years, wins. The star's core collapses inward in fractions of a second. It compresses past the density of an atomic nucleus, past anything our equations can describe, down to a point, a singularity, where density becomes infinite and our mathematics surrenders entirely. What's left isn't an object, it's a wound in the universe. A place where the fabric of space-time didn't just bend, it punctured. And at the edge of that wound there's a boundary called the event horizon. Cross it, and the geometry of space-time becomes so distorted that every possible direction, including time itself, points inward. There is no out. There is no escape vector. Not because something is pulling you, but because the structure of space itself only leads deeper. You don't fall into a black hole. The concept of falling implies movement through space. Inside a black hole, space has stopped working the way that word requires. Now, imagine two of these wounds drifting toward each other across billions of light years of darkness. Binary black holes, two black holes locked in mutual orbit, are not rare. We now know they form regularly when massive binary star systems both collapse. These pairs can orbit each other for millions, sometimes billions of years. Gradually, patiently, losing tiny amounts of energy with each loop around their shared center. Where does that energy go? This is where things get strange. Einstein's theory of general relativity back in 1916, that accelerating masses should create ripples in space-time. Think of it like this. Drop a stone into still water. The disturbance radiates outward in waves. Now imagine that the water is the fabric of the universe itself, and the stone is a black hole moving through it. The ripples that spread outward aren't waves in water. They're waves in the geometry of reality. Gravitational waves. They travel at the speed of light. They pass through everything, matter, planets, entire galaxies, without slowing down, without being absorbed, without leaving a trace. They stretch and squeeze space as they move, but by amounts so impossibly small that for decades, Einstein himself doubted they could ever be detected. He thought they were a mathematical curiosity, a consequence of the equations that nature would render undetectable in practice. He was almost right. As two black holes spiral inward, they radiate gravitational waves continuously. Each wave carries a whisper of energy away from the system, and with each whisper, the black holes draw fractionally closer. This process takes millions of years, then hundreds of thousands, then thousands, then years, then months, then days, and then comes the final plunge. In the last few seconds before two black holes merge, something extraordinary happens to the fabric of space-time around them. They stop spiraling slowly. They begin whipping around each other at a significant fraction of the speed of light. The gravitational waves they're producing are no longer whispers. They become a roar, a crescendo space-time distortion that builds in frequency and amplitude as the two objects accelerate toward each other. Physicists call this phase the inspiral, and the wave pattern it produces has a shape that's immediately recognizable once you know what to look for. It chirps, the frequency rises, the amplitude swells, and then, in a single violet moment, it peaks. That peak is the merger, two singularities, two gravitational wounds in the fabric of the universe, touching, combining. The event horizons stretch toward each other, distort into wild asymmetric shapes, and then snap together into a single unified boundary. The energy released in that fraction of a second is almost impossible to contextualize. For a brief moment, the power output of the collision exceeds the combined light output of every star in the observable universe, and yet you would see absolutely nothing. No light, no explosion, nothing visible to any telescope ever built. Just space-time screaming. The newly formed black hole, larger now, more massive, doesn't immediately settle into a calm sphere. It wobbles. It rings like a struck bell, distorted and asymmetric, radiating gravitational waves as it shakes itself into equilibrium. Physicists have a name for this phase, too. They call it ringdown, and the shape of those ringdown waves carries a fingerprint, a mathematical signature of the final black hole's mass and spin, which brings us to September 14th, 2015. The signal arrived at 5:51 in the morning, Eastern Time. Two facilities, one in Livingston, Louisiana, and one in Hanford, Washington. Both registered the same disturbance within 7 milliseconds of each other. The signal lasted less than a quarter of a second. It rose in frequency, peaked, and faded. The computers flagged it. The scientists were called, and within hours, the realization began to settle in. This was it. This was the signal they had been building toward for 40 years. LIGO, the Laser Interferometer Gravitational Wave Observatory, is one of the most precise scientific instruments ever constructed. Each detector has two arms, each exactly 4 kilometers long, arranged in an L shape. A laser is split down both arms simultaneously, bounces off mirrors at the far ends, and returns to the center. Under normal circumstances, the two beams cancel each other perfectly when they recombine. They're tuned to a precise equilibrium. But when a gravitational wave passes through, it stretches one arm and squeezes the other, simultaneously, alternately by an amount smaller than 1/10,000th the diameter of a proton. That's not a typo. That is the scale of sensitivity required, and the mirrors detect it. The interference pattern shifts, the equilibrium breaks, and the signal is recorded. The event designated GW5914 came from two black holes, one 29 times the mass of our Sun, one 36 times that had merged 1.3 billion years ago. The gravitational waves from that merger had been traveling through the universe ever since, crossing billions of light years of empty space, passing through galaxies, through nebulae, through the solar system, through the Earth itself, and finally, on a quiet Tuesday morning, they caused two 4-kilometer laser beams to wobble by a distance too small to have a meaningful comparison. Einstein was right. The universe speaks in gravitational waves, and we had finally learned to listen. But here's where the story takes a turn, because as LIGO kept running, as more events were detected, neutron-star mergers, black hole collisions, a growing catalog of cosmic catastrophes recorded in the language of space-time ripples, physicists started comparing the signals to their models, running the numbers, cross-referencing the ring-down signatures with their predictions. And they found something that didn't fit a signal. From a particularly massive black hole merger, produced ring-down waves that were slightly, subtly, but measurably different from what general relativity predicted. Not drastically different, not obviously wrong, but wrong in a way that was consistent, reproducible, not noise. The black hole wasn't ringing the way it should. Now in science, a slight discrepancy can mean one of several things. It can mean measurement error. It can mean a poorly understood variable. The environments around massive black holes are complicated, chaotic places. Or it can mean something far more interesting. It can mean the model is incomplete. General relativity has passed every test we've ever thrown at it for over a century. It predicted Mercury's orbit. It predicted gravitational lensing. It predicted the expansion of the universe. It predicted gravitational waves themselves decades before we could detect them. It is, by any measure, the most successful theory of gravity ever constructed. But it is not a complete theory of everything, and physicists have known for decades that it breaks down in exactly one place. The singularity, at the center of a black hole, or rather at the point where a black hole's interior collapses to infinite density, general relativity produces nonsense. Division by zero. Infinities. The equations fail. And for decades, the working assumption was that this was a problem to be solved later because whatever happened inside the event horizon stayed inside the event horizon, undetectable, irrelevant to anything we could ever observe. But what if that assumption is wrong? What if whatever is happening at the singularity, whatever quantum effects, whatever exotic physics, whatever unknown structure leaks into the ring down? What if the way a black hole vibrates after a merger carries a faint, but measurable imprint of the physics operating at its core? That is what some physicists now believe they're seeing in the signal, not an error, not noise, an echo. The idea has a name, gravitational wave echoes, and it's one of the most controversial and exciting concepts in modern physics. The standard picture of a black hole interior ends at the singularity, a point of infinite density with no further structure. But several competing theories of quantum gravity, including string theory-inspired models and Luke quantum gravity, predict that the singularity is not actually a point of infinite density. They predict that at scales smaller than anything we can currently probe, the classical geometry breaks down and something else takes over. A quantum bounce, a Planck star, a firewall, a fuzzball. The names differ, the predictions differ, but many of them share one feature. They replace the classical singularity with a compact structured object, and that structure would reflect gravitational waves differently than a classical black hole interior. The merger happens. The ring down begins. The classical signal fades, and then, after a delay determined by the size of the compact interior, the waves bounce back. They echo. They re-emerge from the black hole with a slight delay and a slightly altered profile. Faint, very faint, but potentially detectable by instruments like LIGO. The original analysis of this possibility sparked fierce debate. Some researchers claimed to find tentative statistical hints of echoes in LIGO data. Others ran the same analysis and found nothing beyond what random noise would produce. The debate is ongoing. The data is contested. No consensus has been reached. But here's what isn't contested. If gravitational wave echoes are real, if the signal contains even a faint imprint of the physics operating inside a black hole, then we have found a way to do something that was previously considered fundamentally impossible. We would be seeing inside a black hole, not visually, not directly, but in the same way that you can learn what's inside a bell by listening to how it rings, we would be learning what's inside a black hole by listening to how it vibrates after a collision. The information encoded in that vibration, if we can read it correctly, would be a window into the most extreme physics in the universe. Physics that currently has no working theory. Physics that connects general relativity to quantum mechanics in a regime where neither fully works. The stakes of getting this right or wrong are difficult to overstate, because this isn't just about black holes. It never was. The conflict between general relativity and quantum mechanics is the deepest unsolved problem in fundamental physics. These two theories, each extraordinarily successful in its own domain, are mathematically incompatible. They describe reality differently at a foundational level, and every attempt to unify them has run into walls. The singularity is where that conflict is loudest. It's the place where both theories apply simultaneously and neither works. It's been called a crisis in physics, a wound in our understanding as profound in its own way as the wounds that black holes create in spacetime. Gravitational wave astronomy might be the key that unlocks it, not by building larger particle accelerators, not by devising new theoretical frameworks in isolation, but by listening, by pointing extremely precise laser instruments at quiet rural fields in Louisiana and Washington, and letting the universe tell us what it's made of, by translating the screams of colliding black holes into data, by looking for echoes in the aftermath. Every 6 months, LIGO and its international partners, Virgo in Italy, Kagra in Japan, grow more sensitive. Every upgrade pushes detection thresholds lower, makes the instruments quieter, increases the chance of catching fainter signals in the ring-down noise. The next generation of gravitational wave detectors, including a space-based observatory called LISA, planned for the 2030s, will be millions of kilometers long, dwarfing anything on Earth, sensitive to frequencies and events that current detectors can't touch. We are at the very beginning of gravitational wave astronomy. We have heard so far a handful of notes, and already one of them sounds wrong in a way that might mean everything.